Hey everyone, so for this video I want to kind of talk through the normal distribution a little bit and specifically doing some calculations using our TI calculator. How can we find different areas under the normal curve or find a value given a area or a percentile? So the normal distribution is something we see all around us. Natural things like measurements of people or plants, things like that, typically come out normal. A lot of the time, for example, we have some birth weights here. So you can see the average baby weight is like 3.5 kilograms, it's like 7 or 8 pounds. And as we get away from that center, very heavy or very light babies become increasingly rare. And this data is not perfect, as you'll see with most data we call normal-ish, roughly normal. But it does fit pretty nicely under this curve, nice enough for us to make some pretty good predictions. The normal distribution is so important, so fundamental to this idea of statistics that it is actually, or was, on the 10 Deutsche Mark banknote in Germany before they adopted the euro. You can see Gauss, the guy who invented this, and there's our normal curve. You can even see the equation there for a normal curve. So there's a couple different things we're going to be looking at with the normal curve. There's a rule of thumb that we'll use called the empirical rule. Your book also calls this the 68, 95, 99.7 rule. So basically what this says is that in a normal distribution, 68% of the data is within one standard deviation of the average. Okay, so if you get more than one standard deviation away from average, right, that's already pretty rare. Within 2 standard deviations of the average contains 95% of the data, and then within 3 standard deviations contains almost all the data, 99.7. So we're going to use the idea of the normal curve to answer a question like this. It says Tacko Fall and Brittany Griner are the tallest players in their league. So we obviously can see that Tacko is taller, but if we wanted to compare them to their own league instead of to each other, that seems more fair and gives an idea of how they stack up against their competition. So we can use the normal distribution to approach this problem because the heights of basketball players comes out pretty normal. Again, it's not perfectly normal, but it's close enough that we can get some pretty good calculations by assuming that it's normal. So in the NBA, players' heights are between 70 or have an average of 79 inches with a standard deviation of 3.5 inches. In the WNBA, the mean is 6 feet, 72 inches, with a standard deviation of 2. Cool. So the NBA, we said, was normally distributed with a mean of 79, a standard deviation of 3.5. This is a really common way to describe a distribution. Normal, mean, standard deviation. You'll see this notation throughout the class. Okay, the WNBA, I'll do a different color, is also roughly normal with an average of 72 and a standard deviation of 2 inches. Cool. So when we're looking at the curve, we have this perfectly symmetric curve, so we know our average is going to be in the dead center, 79 inches. And then each one of these markings here, and you won't always see those markings laid out for you, but I've laid them out to make it more clear. Each one of those markings represents one standard deviation. Okay, so 3.5 inches away. So that means this line would be 82.5. We go another standard deviation, another 3.5 inches, we get to 86, and then 89.5. Cool, so each one of these gaps is the same distance, represents one standard deviation. When you're looking at a normal curve, you can predict where that first standard deviation distance is by looking for something called the inflection point. If you've taken calculus, you'll know what that means. It's where we go from being concave down to concave up. Right, you can see the slope hits this critical point where we start slowing down. All right, but that's not super important. Okay, so let's figure out where's Tacko. Tacko is big, 7'5". Okay, so that's 89 inches. So 89 inches puts Tacko predictably near the very top. 89, that's our boy Tacko. All right, so we can predict where Tacko is. We can describe where Tacko is, rather, using something called a z-score. We know z-scores is where we take the observation, in this case Taco, we subtract the mean, and then we divide by the standard deviation. So essentially it's going to tell us how many standard deviations away from the center Taco is. We can already see what the answer is going to be. It's more than 2, but less than 3. So I'm looking at like 2.75 maybe. Let's do our calculations. So z-score for Taco, 89 minus the average of 79 divided by 3.5. We get 10 over 3.5, 2.86. All right, so Taco's z-score is 2.86, positive 2.86, meaning he is 2.86 standard deviations above average. Okay, we can do the same thing for Brittney Griner. So let's fill out our chart a little bit. This one's a little bit easier to do. Okay, we said that Brittney Griner was 6'8". Yeah. Okay, so that's big. That's 80 inches. So Brittney Griner would be right here, 80 inches. So this individual point, this is our x, right? This is our observation. We could label it xg for x Griner or whatever, but that's the point we're looking at. We can see that 80, without even doing the calculations, is exactly 4 standard deviations above the average. So the z-score for Brittney Griner would be 4. Notice we didn't have to do any calculations because we landed exactly on one of these standard deviations away. Cool. So although Taco is much taller than Brittney Griner, relative to the rest of their league, their respective leagues, Griner's height is more rare. Okay, so he has a z-score of 4 compared to Taco's 2.86. We can answer some more complicated questions, like what % of NBA players are shorter than 6 feet? So let's go back to our NBA distribution here. And let's finish filling this out here. 268.5. Yeah. Okay, so 6 feet is 72 inches. So this is our cutoff. This is 6 feet. We want to know what % of players, what proportion of this distribution is below that line, is 72 or lower. So when we're talking about a density curve like the normal curve, the area under the curve, the whole area underneath that curve, is equal to 100%. And one of the common things we will want to do is to look at a certain interval, a lot of times looking at something on the end like this. We want to ask what proportion of the curve, what proportion is this chunk? In other words, what % of all the players are shorter than 6 feet? So there's a couple different ways to solve this problem. I'm going to talk you through all of them. So the first way to do that is to use the rule of thumb, the empirical rule that we talked about earlier. Earlier we said the 68, 95, 99.7 rule tells us that 95% of our data is within 2 standard deviations. So if 95% of the data is in that middle chunk, that leaves 5% for the 2 outside chunks. So if we take that 5%, we split it in half because it's symmetric, we've got 2.5% on this side and 2.5% on this side outside of 2 standard deviations. Let me get rid of some of those junk here. All right, I shouldn't say percent and proportion together. I should just pick one and go with it. So our proportion is 0.025, which would be 2.5%. So about 2.5% of NBA players are shorter than 6 feet. And like I said, the data is not perfectly normal. This is just using this typical distribution to make a prediction. If we actually went and looked and counted, depending on our data source, we'd actually find it's more like 1.9% is shorter than 6 feet. All right, there's some other ways to answer this problem. So we use the empirical rule here. Another way, another method is to use our calculator, which I'll show you in a minute. And we can also use table A. All right, so in Canvas, you can look at your formula chart and you'll see that not only are you given a bunch of formulas for this test, you're also given some tables. The first table, table A, is all about the normal distribution. So we wanted a z-score of 2, -2, because that's where 6 feet falls in this distribution. 2 standard deviations below the mean. So if we're looking for a z-score of -2, we can locate z of -2, and we're going to use this first number because we want exactly -2.0. So we get 2.28%, about 2.3%. Really, really similar to what we got using the empirical rule. All right, we said 2.5%. The table says 2.3%. Those are close enough that it's okay. You're going to see a little bit of a difference depending on which method you use. Cool. These tables are a little bit hard to read, and for the most part, we won't really use them because we have a calculator. And this calculator will allow us to approach this problem really, really quickly. So to do normal calculations in your calculator, you're going to use the distribution button. So it's right here behind vars, variables. And we're going to use normal CDF, this second option here. Cool. So we're looking at 6 feet. So we're looking at the interval from 6 feet to forever. So when you type in your normal CDF, we're just typing in an interval. So I want to know what proportion of this curve is between 72 and negative big number. All right, it doesn't matter what number we put in here. We're just going to make it so far down that it's totally inconceivable for a data point to fall outside of the lower bound. All right, so I just usually use a really big number. Then we put in our average, 79, our standard deviation, and the calculator will tell us our answer, 2.3%. Really similar to what we saw in table A, pretty similar to what we saw with the empirical rule. The nice thing about normal CDF is it makes it really easy to do more complicated calculations, like what proportion of NBA players are between 73 and 76 inches, right? What would this interval, what would this proportion be? That would be a little bit tougher to do with table A. We could do it, but we'd have to find 2 different values and then subtract them. But it's pretty straightforward with this, right? We said between 73 and 76, I think is what I said. So the TI calculators can do a really good job of finding that proportion. So that little chunk that I've just outlined really quickly is about 15% of the total curve. All right, so the next thing I want to look at, okay, getting all the things right here. So you'll find these instructions embedded in the slides. You can come back to look at those. What if we wanted to ask a question like, what proportion of players are over 7 feet tall? And then here's a new type of question. So we already know how to do that one. Here's a new type of question. A new NBA player is at the 19th percentile for height. How tall is he? So we can answer this question with a calculator as well. We can also use table A, but it gets a little bit harder to answer this question. So if he's at the 19th percentile, so we want to figure out what point leaves 19% of the data behind. And it's going to be hard to figure this out exactly. I'm just going to guesstimate. I don't know where it would be. I could think hard about this and figure out based on the empirical rule. Yeah, I think it's going to be like right here. I'm thinking the 19th percentile is going to be right over 2 standard deviations. I could be totally wrong, but I'm just going to take a guess. So I want to know what x value, I don't really know where it is, what x value on this number line, what mystery x would give us a proportion of 19.19. Right, that would be the 19th percentile if 19% of the data was below this point. So you can also use the calculator for this. It's going to be a slightly different process. We still go to distributions. This time we're going to inverse norm. Okay, so we're working backwards here. We already know what area we want. We want 0.19. And then we can put in our mean and standard deviation as well. Cool, and we get 75.9. So this new player, X, his height is 75.9 inches, which, yeah, I was about right, that estimate. Cool. So whether we're trying to figure out what proportion lies in a certain interval with normal CDF, or we're trying to figure out what X value would give us a certain proportion we can use our calculator to really quickly get to those answers. We could have also used table A for this. I'd have to look through here and find 0.19. Okay, so we'd have to find 0.19. Okay, here we go. 0.19 is at somewhere between negative 0.87 and 0.85. So negative 0.85. Okay, so that tells me, and I got this from table A, negative, write this down before I forget it, 0.875, I think is what I said. Now I've already forgotten. Not quick enough. All right, negative 0.875. I'm saying 75 because it's between 0.87 and 0.88. Again, these tables are a little hard to read at first, but you'll get the hang of it when you kind of analyze it for a little bit. Okay, so in order to get the 19th percentile, we need a z-score of negative 0.875. So if we know the z-score and we know mean and standard deviation, we can get to this value. We can get there, and you can see just from my little bad drawing that this is about negative 0.875 standard deviations below the mean, right? It's not exactly -1, but we're working toward that. Cool, so using table A, we can get to the z-score and then use the z-score to get to x. Again, we're just using the same equation we used earlier for taco. All right, this time we just happen to know what z is and we don't know x, but we can work backwards. Some pretty straightforward algebra. Multiply by 3.5, add 79, and we should get something really close to what we got using the calculator. All right, guys, thanks, and we'll talk about this again next week.